Good morning, everybody. It's my pleasure to introduce today's speaker, Jaroslav Merz from Prague University. He's a visitor he's the first visitor in the IC Early Career Visitor Program, and here to work with me and the SEBE group on red giant binaries. Jaroslav did his PhD at Prague University and in Czech Republic and Košice in Slovakia. And he's here since a month and around for another month. And if you want to speak with him, you're welcome. Now, we are excited about your talk on symbiotic stars in the modern era.
Thank you very much for the introduction. First of all, thank you for coming for this talk and giving me the opportunity to speak about symbiotics. And also, I would like to thank Gaia to giving me the opportunity to come here at the first place, to work with you amazing people here on many interesting topics. What I would speak about is the topic I really love since my start in the astronomical career. It's the symbiotic binaries. So the first part of the talk I would devote to symbiotic binaries as objects, to introduce these binaries to you, because I have found out that symbiotic community is quite small, and outside of the community these binaries are quite unknown. So it would be great if you will take the information from this talk for you to know what these binaries are. And the second part of the talk I will then devote to projects I'm working on, focus mainly on understanding the population as a whole and increasing the sample size, because we know the symbiotics for like 100 years, but still there are many open questions, and we really need to dig into many things still. So to get a picture about symbiotics, this is the most important slide. So if you then would ignore the rest of the talk, you still will have the information about symbiotic. That's the most important. So first of all, these are binary stars. They are very strongly interacting binary stars, and are among the widest interacting systems. In reality, the typical orbital periods of symbiotic binaries are on the order of hundreds of days to thousands of days, even to tens of years. So this is in a contrast with maybe a bit more well-known group of cataclysmic variables, which are like little cousins of symbiotics with orbital periods of few hours. So we are now talking about hundreds of days. One component of a symbiotic binary is a red giant star, so cool and evolved star. And the second component is a hot compact star, which is mostly a white dwarf, but we have some symbiotics even with neutron stars. This is a very simplified model of a symbiotic binary. So you can see that there is a giant, there is a white dwarf, maybe there is some accretion disk, and there is some mass transfer between the components. Still open question is, in what fraction of symbiotics the main mechanism for a mass transfer is via the stellar wind, or in what fraction of symbiotics the giant is actually filling the row slope, so there is a row slope overflow. To illustrate that this is just a simplification of a real symbiotic system, I have a picture of a real symbiotic system. That's one of the closest symbiotic systems. So you can see that in reality the environment is quite complicated, and actually this is Era Aquarii as observed by Hubble Space Telescope. The binary itself is somewhere there in the middle. It's one of the closest symbiotic systems, and really only of few where we were able to resolve the nebula. If you will look into the central part of that system, then you can see with the top modern instruments nowadays, this is taken by Sphere Planet Hunting Instrument on ESO VLT, you can really see two stars. For most of the systems, we are not able to resolve the binary, so we need to have first some other confirmation of the binarity, but we know that symbiotics are binaries because single star models just doesn't explain the data. And then if you would like to study the components, you need to do something more, not just imaging. Another nice example of a symbiotic binary, which has quite nice resolved nebula, is this one. also nicknamed as a Southern Crab Nebula. And you can see that there is a binary itself, and there are some traces of the previous outbursts of the system. And actually, in addition to these lobes, you can see jet features here. So the environment is quite complex for studying. In general, this is a quite heterogeneous group, and therefore it's very complicated then to study this as a sample of as a population, because in symbiotics you have several types of the stars which are there. First of all, the cool component, it's either a normal red or yellow giant, and you can quite well then see that in a spectra and in the infrared part of the spectra. And therefore, we call these symbiotics as S-type symbiotics, because this is a stellar type, we can see the star. But in some of the cases, you have a Myra pulsator in a symbiotic star, so a bit more evolved. You have a lot of dust, so you don't see that well directly in the optical spectrum, the cool component. So therefore, we call these stars D-types, dusty types, symbiotic stars. And actually, the Myra itself is a symbiotic star. So maybe you will, you didn't know that, but Myra is one example of this type of symbiotic star. You can see that contribution from a dust when you have this multi-frequency spectral energy distribution. So in a S-type symbiotic, it's just dominated by the stellar photosphere, while in the D-types, there is some contribution of a hot dust or warm dust in the near infrared and far away. And then this important part of a symbiotic binary is also the hot component, because all these nice things in symbiotics are ongoing, especially in the vicinity or on the hot component. And in general, also in this case, we have a bit heterogeneous group of hot components. At one place, these are quite luminous white dwarfs in so-called shell burning symbiotic stars. In this case, we mean by the shell burning that there is ongoing surface shell burning on the surface of the white dwarf. But also quite recently, it was found that there is probably a big group of symbiotics which don't have this surface shell burning on the surface of the white dwarf. So either they have a faint white dwarfs or even neutron stars, and the luminosity of that is powered by accretion only, so you don't have this another component by the shell burning. So this we call accreting only symbiotics. If you will go to the literature from the last century, you will, and maybe even today, you will find that also main sequence accretors were considered as hot components for symbiotics. The problem is, I don't consider this as symbiotics, just for a simple reason that binary, which would have a red giant and a main sequence star, would be in completely different evolutionary point than a star where one of the components is evolved towards white dwarf and the second is already left the main sequence and it's a red giant. So even in the recent literature, this is somehow now not considered as a symbiotic binary as we use that term. Some of these binaries are really interacting binaries in the first episode of the mass transfer. And you will find all the names like symbiotic binaries in the first episode of the mass transfer, pre-symbiotic binaries. I would not go into much more details, but most of the community now focuses on and considers symbiotics those which have a red giant component and a white dwarf or neutron star. The stellar components of a symbiotic binary are very different from each other in a sense of a temperature mainly. So you can see that the giant, that's the blue, is dominating into the optical and near infrared part of the spectrum, while the hot component is usually dominating the short wavelengths. You have a contribution from a nebula as well, and if you are and of the dust, if that's a dusty type symbiotic star, so that's just a sketch. What you can see when you obtain an optical spectrum is that the flux is basically dominated by the giant. So you can see, for example, this very nice molecular bands. So you see a cool star in the spectrum, but in addition to that, you see the contribution from a nebula, and you see a lot of emission lines. And that's actually how symbiotics were discovered also in past, and what gave the name to this class of binaries, because you see basically in the optical, you see the cool star and emission lines, which were known only from the hottest stars observed, so with a very high ionization potential. So the first name was then stars with combination spectra, and then symbiotic stars in early 1940s. The problem is that not all symbiotics are behaving nicely like that you can really, from the optical spectrum, easily say that it's a symbiotic star. This is a shell-burning symbiotic star, so you can really see a lot of emission lines. You can see contribution from a nebula. You can see even the contribution from a hot component if you are in UV. The problem is that with accreting only symbiotics, many of them in optical spectrum looks just like a normal giant. So to get that evidence for symbiotic nature, you need to look for some other indirect evidences, not from which you will not get from the optical spectrum. So if you can have a UV spectrum, that helps, but it's just not that easy to get a UV spectrum for a star nowadays. But also you can see, you can try to search for some evidences of the ongoing accretion. I will talk about that a bit later. So the variety of the symbiotic spectra, this is just an illustration of few of the stars. So you can see that for yellow symbiotics, you don't have molecular bands, then you are going to lower temperatures. So the molecular bands are more prominent, but what is just the feature you are looking for, especially in shell-burning symbiotics, are very prominent emission lines of species with like high ionization. So, for example, one thing which is very helpful is to search for example, for helium-2, which you would not expect to see in a single cool giant in emission. So, if you have a spectrum of a cool giant with helium-2, you know that it probably, or most probably, it is a symbiotic star. In D types, you don't see the cool giant directly in the spectrum. So that's actually the connection with planetary nebula people, because this just reminds a PN spectrum, and actually many symbiotics in past were discovered or were first considered planetary nebulas. And just then it was found that there is a giant when the first infrared surveys came. So they were then reclassified as symbiotic stars. In accreting only symbiotics, you see that this is very hard to distinguish between single giant and symbiotic star based on the optical spectrum only. The last one is with the neutron star accretors. These are with white dwarf accretors, but just they reminds a lot just a single red giants. This is an illustration of light curves of symbiotics. These are long-term light curves, so it's 30 years, which is shown here. And you can see that a lot of things is going on in symbiotics. Light curves are very complex. The reason for that is that you can see several effects at once, basically, in the light curves. So there is something which is connected with the orbital motion. So you can either see some reflection effect and you see some kind of sinusoidal variation with the orbital period. In some cases, you can even see eclipses. So that effect is repeating with the orbital period. But then in many cases, you can see, and this is just a clear example of pulsations of the cool component, but in many other cases, when you study like multicolor data, you can see that the orbital motion is better detectable at shorter wavelength, and if you go to longer wavelength, you just see the pulsations of a giant. So if you have just one filter, as is now quite typical for many surveys like Assassin, then you have things which are a bit more complicated in comparison when you have like 5 filters or something like that. And in addition to these basically 2 groups of effects you have connected with orbital motion and pulsations of the cool component, what you can see are the effects of the mass transfer itself. So the outbursts and active stages. So you can, for example, see on these 3 or 4 first cases that there are some like quiescent stages, and then you have some active stages with several outbursts. And what we know is that actually the outbursts are like not similar, or not the behavior is not the same between the individual symbiotics. So, for example, in AG Pegasi, we have detected during these 30 years just 1 outburst. In AG Draconis, there are 3 active stages. In Z Andromeda, there is 1 long. And even when you look at one object, the behavior is changing a bit. So the active stages are not the same even for one object. But these symbiotic stars are showing the outbursts which we classify as classical symbiotic outbursts, or Z Andromeda type, that's a prototype, which is actually the most common group of symbiotics showing outbursts and least understood group of outbursts. But then we also have some objects which have a different type of outburst, like Rs of Yuhi, that's a symbiotic recurrent nova. So you see that really that the behavior, the outburst behavior is a bit different if you compare that with the top light curves. And also we have so-called slow symbiotic nova, which showed outbursts which are lasting for decades actually. So at least these three groups. And what you cannot see on the time scale of 30 years, but if you will study the time scale of a few hours, you will see that you can see some evidence of accretion in the form of so-called flickering, which is stochastic variability connected with the accretion and with the fact that it's not a smooth process, so that flow is just not like completely smooth. So there are some changes in the brightness on the time scale of few minutes. And again, at the end of the talk, I will mention that again. So why these objects are important? I think if you will be listening to any talk and people speaking about their objects of interest, they will say that they are important for astrophysics. That's just a general feature of any talk. But also symbiotics are unique astrophysical laboratories for the reason that basically you can study a lot of processes which are still like poorly understood and are applicable for a large number of other classes of objects in one system. So you can see the stellar interaction, the interplay between mass transfer and accretion processes. You can study the stellar winds and actually their collision in the system. You can study the formation and collimation of jets. You can study the dust, the outburst, thermonuclear outbursts in the systems. You can then apply the knowledge from symbiotics also to cataclysmic variables and so on. And of course, as all the other binaries, they are important for stellar evolution, and not only for understanding the evolution of stars, but especially to understand the evolution of binaries and the phases of the evolution, which are still not very well understood. And just to mention again some connection with other fields like cosmology, the symbiotics were proposed as one of the possible progenitors of supernova 1As. So the question is how big the contribution can be, but it's one of the promising channels for 1A supernovas. And there are many open questions connected with the evolution of symbiotics itself, with the pre-symbiotic and post-symbiotic life, with supernova 1As, with connection with the common envelope binaries, because and gravitational wave sources. As I mentioned, still very poorly understood is the mass transfer in symbiotic binaries and the fraction of Roche lobe filling giants. And if you don't understand that precisely, then it's very hard to get from some models the orbital and stellar parameters. So just as an example, this is a comparison what model predicts That's the orange and blue lines, just two different models. And what we observe for symbiotics, that's shown in gray. So for orbital periods, the symbiotics should not be where we observe them. Most of them should have longer orbital periods, but they just don't. And also, this is just a mass ratio of symbiotics. Basically, where you would expect symbiotics, there are not many of them, and they are everywhere else, but not where you expect them. But that's a problem that we still don't know how the mass transfer is ongoing and how to get to that symbiotic stage. So which parameters just lead to symbiotic phenomenon. And of course, with that is connected that if you are unsure in these parameters, you just cannot very well predict the size of the population in a galaxy. And with that is connected that if you don't know what the size of the population is, so you cannot tell how much symbiotics can contribute to supernova 1As, because you just don't know how many of them are in good progenitors of that. Even like with the accreting only symbiotics, it's very hard to detect them. So all the catalogs are biased towards shell burning symbiotics. And as I mentioned, still the debate is ongoing also with the outburst mechanisms of symbiotics. While for symbiotic recurrent novae or slow symbiotic novae, that's thermonuclear outbursts, which can be modeled quite well. With classical symbiotic stars, this kind of model will not work because you just have very short recurrent time scales on a not very massive white burst, so it's just not physically possible. So there is something else which you need to add to the models, and that's still not very well understood. So now I will continue with the project I'm working on, projects I'm working on, and especially to address some of the questions I have mentioned. So the first thing, when I started my PhD, I realized that we base all the research on symbiotics on the catalog, which was published in 2000. It was, I don't know, 2017 when I started, I don't remember. So the catalog was basically like 20 years old at that time. And many other objects were discovered since then. So to understand the population, you would like to include them. So that one in 2000 contained only a bit more than 200 objects, including some candidates. 30 of them were considered just candidates, and 17 extragalactic symbiotic stars. So my idea was to create something new, something complex, a bit more modern that the catalog published in 2000, and to be able to, or not, you know, if you publish just a list or catalog in a paper, it will be outdated at the time of the publication. Definitely, it was the case for this one. So to have also the online version of that catalog, to be able to update that catalog, include new information, include new objects, move the objects from one category to another. I will just mention that in a second. So I created an online database of symbiotic variables. There are two mirrors for the database. You will find the same database at both links. The reason was just that for some reason it was not possible, for example, to the server in Slovakia for people from South America to connect to the server. It was just rejecting the questions. There were some problems with hackers last February. And probably there is some policy that is just blocking the connection from the strange countries. I don't know. So therefore, there are two mirrors. So everyone should be able to at least access one of these. I have a bit more objects than in 2000 in the catalog. So actually, in our galaxy, now the number of the objects is more than 1,000. This number consists of confirmed symbiotic stars. So for those we are pretty sure these are symbiotics. There is some number of candidates. And also I am keeping a list of objects which were considered symbiotics and were reclassified afterwards. I think this is very important because when I was working on this database, I was reading a lot of papers, actually, like 10,000 or so, just to get the extract information from that about the symbiotics. And I have found that several times it happens that you have an object which is considered a symbiotic star, then it's reclassified as something completely else. But then, you know, in Symbiot, it's still confirmed, for example, and then people take that for information, and again, it's considered a confirmed symbiotic star. So, and then this is somehow polluting the sample, and then when you use the sample, you have 10% of objects which are not symbiotics, and that's causing troubles. And in addition to objects in our galaxy, now we have 183 objects in external galaxies, and actually in 16 external galaxies. 70 of them are confirmed. So as I mentioned, I'm keeping the list of the confirmed objects, misclassified objects, and of the candidates, that's the number in the middle. But even for the candidates, there are like 3 groups in the database for likely, possible, and suspected. Just to distinguish between the objects which are very good candidates, we have a lot of data for them. They are not completely fulfilling the definition of a symbiotic star, just because, for example, we don't see highly ionized emission lines, but we are almost sure these are symbiotics. So these are likely candidates. From the objects which someone in the literature said, that's a symbiotic star because it's a red star. And that's a real case of some symbiotic candidates, that they are considered symbiotic stars in the literature just because it's red, so it's symbiotic. So that's the list of suspected candidates. That's the lowest classification of the candidates. Of course, as any catalog, you have tables with data. A lot of tables with a lot of data. So for all the classes, you can filter out everything, and you have some data, a lot of columns, and even some parameters of orbital stellar parameters. You have identifiers, you have cross match with other symbiotic catalogs, and so on. That's available in a tabular form. But also, I decided to have for every object which is in the database, so now we are almost 1,400 objects, there is a object page where you have all the information on that object with the references. So any information which is there, you can just click on the reference and you will be taken to ADS where that information was set. So here you have like all the information, you have also some notes, you have some links, and so on. And the other part of the database is also that I am maintaining a special list of symbiotics which are detected in outbursts. So if you are interested in having just those which are detected in outbursts and which type of outbursts they were detected, there is a special list. Symbiotics detected in X-rays with the X-ray type. There is a classification for symbiotic stars in X-rays. Symbiotics with detected flickering, which I mentioned is that accretion feature. Symbiotics with detected jets, and symbiotics with resolved nebulae. So everything you will find on the website of the database. It was first released as a beta test in 2019, and new version was released early 2023. That first release was to get feedback from the symbiotic community, but it seems that the database is now quite widely accepted, and it was referenced already 39 times. There is one new citation from today morning. What is important is that it's actually the most comprehensive collection ever published of stellar and orbital and other observational parameters of the symbiotic stars. So you can really analyze the symbiotic population as a whole. I will show that a bit on the next slides. And the sample can also be used as an input for further research. So for example, to search for new symbiotic stars, you have a sample of known objects, so you can get information what you are looking for machine learning and so on. So I will not talk about the parameters of the symbiotics in many details, because it's just not probably that much interesting at this point. But just to show that, for example, now we have a quite large collection of orbital periods for symbiotic stars, and really you can see now the trends, which we were able to see even like 20 years ago, but the number was not 30, but it was somewhere like 5, for example. So there was suspicion that the periods are shorter than expected, but now I think we have a quite large sample to confirm that. And that's true for many other parameters, that we can draw new conclusions from that, but also to confirm what people were thinking, but were not sure with a smaller sample in past. So for example, with the cool giants, you can see that there is also a very high concentration of symbiotic stars with quite late spectral types. We can now say something about the metallicity of the symbiotic stars. This is not important at this point. Actually, the blue ones here are S-types. These are D-types. There is a group which I did not mention on purpose, because it's just a very small group, which contain G-type G-type cool giants. So that's red. And also it's valid for this one, but by green here, I wanted to mention that here these are K-type giants. So what was actually found, that for most of the symbiotics hosting M-type giants, you are around solar metallicity or a bit slightly lower, in contrast with expectation, because people actually thought that symbiotic giants are metal-rich giants. Probably not. But all K-type symbiotic stars host metal-poor giants, so that it can be very well seen here. And also many symbiotic stars show some pulsations. In most of the S-types, these are either semi-regular pulsations or so-called OSARCs. These are ogle, small amplitude, red giants. Basically the same phenomenon as a semi-regular variability, just on the smaller amplitude and shorter time scales. And some of them show Myra pulsations, especially those which are found in the D-types. Just another figure for hot components. You can see that they cluster somewhere around where you would expect the central stars of planetary nebulas, actually. So that's another connection with PNs. They are pretty hot because, especially those which are showing the shell burning, these are these purple ones. They're pretty hot and pretty luminous because of this shell burning, while the accretion-only systems usually have much lower luminosities, or their hot components have much lower luminosities. So you can also see that pretty well here. And as I said, you will find many more in the database, so you can search for what is interesting for you there. Here is in galactic coordinates where the symbiotic stars are located. The blue ones are confirmed, the red ones are candidates. You see that they cluster at some regions. Of course, the concentration of stars is very high there, so you would expect that that will happen. But there is also some small bias because of the surveys searching for symbiotics in the last decade or two. We're just focusing on those regions. So maybe now with the Gaia, I will just mention that in a minute, that we can search for symbiotics all sky, not only in the regions around the galactic plane or galactic bulge. The problem is that I mentioned that we now have 283 confirmed symbiotic stars in our galaxy. It's a bit less than expected still. So they are still there somewhere, hiding probably. So you see that the numbers start somewhere around like few thousand, are going to few hundred thousands of symbiotic stars. So we are still missing probably a large part of the population. And that's very important to find these symbiotics, because then we will probably be able to get rid of the biases in the sample. So one of the ways was to study the candidates from the database, because many times it's just either candidates from surveys or 5 minutes. Candidates from surveys or just were found as a byproduct but not studied in details. So to first clean the database from the incorrectly classified objects and to increase the size of the confirmed ones, we created a program collecting the data from the surveys like Gaia, that's a very important ingredient, and also others, to study first like multi-frequency photometric data on these long-term light curves to get the astrometry, and for symbiotic classification, it's very important to have also spectroscopic information, to at least a single epoch spectrum for the classification. If that object is interesting, we are usually following that for longer time, but for classification, at least a single epoch optical spectrum is needed. This is again just an example that how the spectra we obtain for some of the objects. You can go through this list of papers if you are more interested on this project, but we studied optical spectra, we studied spectral energy distributions, we focused on light curves as long-term as possible, and also then you can have some hints from other evidences which are a bit more indirect, so you cannot use just the position in a HR diagram as a confirmation of a symbiotic status. But if that object is lying on a main sequence, that's a very good evidence for non-symbiotic nature of an object. So in blue, you see where confirmed symbiotic stars are lying, so it's somewhere among the giants. In Gaia, the reason is that the Gaia filters take most of the flux from the giants, so the contribution of a hot component or a nebula is not that significant in the Gaia filters. So this is Gaia HR diagram, and also you can use another information, for example, from infrared, from TUMAS survey, because also symbiotic stars, S-type symbiotic stars and D-type symbiotic stars can be distinguished, for example, from cataclysmics or some BE stars or planetary nebula. They lie in the different regions. But again, it's not a full confirmation of a symbiotic status. It's just another hint you have. So I will not go through all the objects. I would like to just show you some interesting objects from the sample for several reasons. For example, this one was object which was actually observed in outbursts. In two outbursts, in 1926 and 1983, but nobody never have obtained a spectrum to confirm the symbiotic status. We were the first after like 40 years to obtain the spectrum, and we confirmed that it's a yellow symbiotic star. It's a very easy target, but we have several like this in a sample. Another one, and that's actually a paper which was accepted last week, so you can find it on arXiv already. It was classified as RCRB variable based on the light curve in 1940. A spectrum was obtained. It was showing hydrogen in emission. You would not expect to see hydrogen in emission in RCRB stars. So it was classified as a possible symbiotic star. It was 1989. The problem was that that spectrum was not showing any highly ionized emission lines, so no definite confirmation of a symbiotic status. The reason why it was not showing highly ionized emission lines is that it was in accreting only state, because now we know that it's a symbiotic nova, and it's currently in the outburst, and it seems that it might be a first symbiotic nova detected in repeated slow symbiotic outbursts. So quite interesting object we have found in the sample. Not always we are that successful to confirm symbiotic status. Sometimes we just need to reject the nature. So for example, this one was classified as a symbiotic star just based on the photometric appearance. During the search for post-AGB stars, we found out that it's a WUMA variable with a period of 0.33 days, so not a symbiotic star. Another one was classified as a, I still have enough time. I was set 45 minutes. So this was classified as X-ray source, and then detected as an X-ray source is classified as a possible symbiotic binary, cataclysmic variable, supernova remnant, H2 region, everything in the field of this galaxy. Unfortunately, it's just a foreground active young red dwarf, not a symbiotic star. And another interesting candidates were found in the globular cluster 47 Tucani. There are theoretical predictions that you should find some symbiotic in globular clusters in the outer parts. Not many, but there might be some from the models. So these were classified as symbiotic candidates based on the X-ray detection and some coincidence with the infrared source of a cool star, but unfortunately, we still have no symbiotic star in a globular cluster. So even these are not symbiotic stars. So I will end the search for candidates with the Gaia DR3, because actually Gaia produced a lot of symbiotic candidates. They claim symbiotic stars, but let's consider them as symbiotic candidates based on the machine learning. So they took low-res RP spectra, astrometric data, Gaia photometry, and produced a list of candidates. It's not very well visible, but these are these brown ones. So most of them actually fall in the correct region where you would expect symbiotic stars. You can distinguish quite well with astrometry and RP spectra a cool red giant from something hot or something on a main sequence. And even in the infrared diagram, they fall in the correct region. The problem is that Gaia is also giving you information about detection of emission in age alpha based on a low resolution spectra, so you need to be careful, but still most of these are not showing age alpha in emission. And that's in contrast with a known sample of symbiotic stars, because known sample is in Gaia is showing emission in age alpha, even in Gaia. So in reality, actually just 7 out of this number is showing age alpha. In emission according to Gaia, which is measured from the low resolution spectra. We observed all of them have real detection of H alpha, and some of them are real symbiotic stars. Most of the others are probably just pulsating red giants, because they would show very same behavior in the light curves as symbiotic stars. But it seems that H alpha actually is, the measurement of H alpha from Gaia is usable to identify promising symbiotic stars. We have designed a new method how to do that, and tested that on the emission line stars list from Bray and Henise, and then Gaia LPVs from Gaia DR3, because most of the symbiotic stars show some long periods in the light curves. And we already are at the number of like 30 new symbiotic stars based on the ongoing search, including 2 yellow. That's quite small sample, but even smaller sample is of the carbon symbiotic stars. So we increased the sample size by 20% already. And I think that that's one of the last slides, is that there is also other way how you can use Gaia to search for symbiotics. You can search for symbiotics detected in outbursts, because Gaia is producing so-called Gaia science alerts, so giving you information about objects which are changing in brightness, not only going up, but also fading. We already were successful to detect first outbursts of some, first recorded outbursts of 2 known symbiotic stars, thanks to Gaia. We have detected the eclipsing nature of one object based on the detected fading by Gaia. And also in 2020, we published the first symbiotic star, new discovery of a symbiotic star by Gaia. That's this one. And actually, I like to have the collection of objects. So I have already also a first extragalactic symbiotic star detected by Gaia, and a first Gaia symbiotic nova. So Gaia is quite interesting also from this point of view. So I will finish just with a quick teaser for what I will speak about maybe later when I will come back, or what you will be able probably to read in some paper. in the future. The long-term variability of symbiotics is quite well studied already, based on the many surveys. So you can, as I mentioned, you can study the orbital pulsation and outburst activity of symbiotics. It's not true for short-term variability of symbiotics. There are some efforts to study the short-term variability from ground with the light curves up to few hours. Especially people are searching for signature of accretion, so flickering, as I mentioned. Or in one case, a periodic signal which is taken as evidence for a magnetic white dwarf, so for a rotation of a magnetic white dwarf. But there are test data for many symbiotic stars available, and they have never been studied in details for a large sample of symbiotics. So the idea of the stay here was actually to take a look on the test data. Not only full frames, but we have a short cadence data for many of the symbiotic stars. So the first idea was to search for oscillations of a cool component. These are red giant binaries. People here are working in red giant binaries. So let's try to do that for symbiotics. What we have found in this first week is that actually what looks like oscillations of the cool component is probably flickering, what you can see in the test data, which was a bit unexpected, given that the red test is observing in red part of the optical spectrum. The giant is dominating that part, and the flickering is typically detectable just in blue, where the red giant contribution is not that strong. So one would not expect to see the flickering with tests just because the flux is dominating by the giant and the flickering is connected with the hot component. But actually, it seems it's possible. And this is my last slide, actually, just to show that this is a TCRB, test light curve of TCRB, and we can see the flickering in the light curve of TCRB. So TESS is able to detect flickering. And I hope that we will not only now be able to investigate the flickering in a large sample of symbiotic stars, but also to increase the size of the sample of symbiotics showing flickering, because we are now at the number of 11 confirmed flickering sources in 283 symbiotic stars. With that, I would thank you for the attention, and I will take the questions. I was told that I have 45 minutes for the talk, so
it's actually. Thank you.
It's not.
Thank you for a very nice talk, and I see the database is making impact. Are there any questions in the auditorium about Symbiotic?
So maybe it's a naive question. I just want to understand. For example, in this last symbiotic that you show, T Corona Borealis,
yes,
the flux is actually like going up, no? There is an expected outburst like soon in the next years, we don't know when.
Yeah.
Is this related also with the flickering somehow? I mean, the fact that you have some flickering is related to the fact that you might have an outburst, not?
Not necessarily. It is true that for TCRB, we are awaiting an outburst. In now or next Wednesday, or maybe in 3 years, plus minus.
Yeah.
But we are expecting the symbiotic recurrent nova outburst from TCRB. We know that the flickering is much better detectable from ground. It was detected only in systems which don't show shell burning, so which are in accreting only state. Every accreting only symbiotics would show an outburst once or several times, but the question is if you will need to wait for ages for that, because accreting only symbiotic is just collecting and awaiting an outburst. In shell burning, probably there is a flickering, but you cannot detect it because of the contamination by that burning, which is ongoing. But even with the TCRB or similar symbiotics, we know that there are epochs where the flickering is with much lower amplitude. It's not directly connected with that we are awaiting the outburst. Probably that's connected with the amount of matter which is transferred. But also an outburst can temporarily somehow kill the flickering. So if there is a strong outburst, because flickering is probably coming from the accretion disk around the hot component, the outburst is ongoing on the hot component. So that outburst can destroy the disk, and you will need to wait for the matter just to detect the flickering. So, but I would not say that if you see the flickering, you can await the outburst soon. That's not probably the general conclusion from that.
Okay, thank you.
So first of all, congratulations for the catalog. I cannot imagine the amount of work that you have put on it. So congratulations, and this kind of database are very useful for astronomy. I was wondering for which fraction of the sample do you have an orbital period measurement? Because you were showing us the histogram, and I was wondering if, because of course it's easier to measure the short orbital period system and the long orbital period system, no?
Yeah, there actually was this discussion already in the literature if this could be a selection effect, some kind of, but we have orbital periods for like quite large fraction of the confirmed symbiotics. I don't know the number from top of my head, but it doesn't seem that it's because we just have the short periods. So for most of the relatively bright objects, we have orbital periods, and it doesn't seem that there is a large fraction with longer orbital periods. The problem is probably in the models, not in the observations, that the input into the models, the physics of mass transfer is not fully understood. Actually, still a few years ago, the majority of people thought that most of the symbiotics transfer mass just via the stellar wind. Then infrared light curves were obtained for some objects, and it was found that many show the ellipsoidal effect, which is a suggestion that the giant is deformed, so it might be filling the row slope. You just don't see that in the optical, for example, light curve, because it's dominated by the nebula and you see the reflection effect. So maybe quite large fraction of symbiotics is filling the row slopes. But just, for example, very few were analyzed by interferometry. So yeah, that's one of the plans to study symbiotics with interferometric methods to investigate the fraction.
Thanks for the talk. I have a curiosity and a question. The curiosity is the first, or one of the first images that you showed about our Aquarius with a sphere. Okay. If you can show, because it's a beautiful image.
Yep.
What is the wavelength and the scale of the image? Yeah, that one.
I am not sure. That's not my work, but this is a reference for the paper, so I would just reference you to that paper.
Okay, thank you. I will look for it. Maybe it's in the infrared, I'm not sure. And maybe the scale is super-sec. But
I'm not sure if that would be in infrared, just looking at the relative brightness of the hot component is not that bright in the infrared. So I would guess that that's probably in the optical. But okay, I'm not sure.
The question is about the catalog. It's nice that after 20 years you improve the catalog of Helsinki. But however, you only added maybe 60 or something like that new confirmed symbiotics. Most of them are still more than 700 in your catalog. Are still candidates with different categories, which I personally don't trust too much. And the difference between likely and possible and so on. So my question is, are you planning to do something to really confirm, to do something with the catalog so that you can in the future address the important problem of the population of the symbotics in the galaxy.
Yeah, that's actually what I mentioned in the second part, that I'm already working on that. So to select the candidates from the database, that's one part of the work. Then there is another part to search for completely new unknown objects, but also to go through the candidates. For many of them, it actually would not be very difficult to confirm or reject the symbiotic status because they are quite bright. You just need to get the optical spectra. You can see, for example, as in some of the cases when you have a main sequence G-type star, it's just not a symbiotic star, so you can reject and clean the list of candidates from that. And some of them you can confirm, like I mentioned that one. The two of them which were like known for 40 years. For some of them, I think we will need to wait for much longer to confirm. There are, for example, some symbiotic nova, recurrent nova candidates in, I don't know, it was NGC 300 or something like that, galaxy, which were at the top brightness of a magnitude 25. So nobody will probably ever be able to confirm or observe these objects in quiescence. But many of the candidates, that's a plan actually to really clean the database from the objects which are not symbiotics and to confirm those which are promising candidates for symbiotics.
Okay, so I have one more question on the distribution of binary orbital elements.
Mm-hmm.
You said the simulations show a very different range. What do those simulations take into account?
It's just some population synthesis, which I think that the main problem there is the fraction of symbiotic stars filling the Roche lobe and the stellar wind. That's the mass transfer mechanism is the main problem there. Okay. I guess. Because actually after that it was found that another possible mechanism is that somehow the wind is filling the Roche lobe and then it's more concentrated towards the hot component, some wind Roche lobe overflow mechanism.
Okay, but for that I would actually expect them, because the simulations showed something above 1,000 days.
Yeah.
But for that I would rather expect it below 1,000 days to efficiently have mass transfer.
Yeah, that might be also. Yeah, I think that might be also connected with the like pre-symbiotic evolution in a sense that, you know, when you have that current white dwarf in a red giant stage, then you need to somehow avoid the common envelope evolution and the fact that you cannot just end up with the CV on the orbit of 3 hours. So that would also probably the common envelope evolution would also be a problem.
Yeah, makes sense. Yeah. Okay, so if there are no other questions, we thank the speaker again, and there is also the scientific coffee in the cafeteria. Everybody is invited to, and I think the students get the stamp from you. Okay, we thank Jaroslav.
Thank you.